Hi. So I'd like to talk to you in this lecture about electrostatics, including some fundamentals of charge such as conservation of charge, quantization of charge, and Coulombs Law. So in the natural world, there's two kinds of negative charge. So there's positive charge and negative charge. Now, it's important to remember that this is kind of an arbitrary name, and what was positive and what was negative was kind of signed in an arbitrary way. But what we go with is the convention, which is that negative charges are the type of charge possessed by electrons, and that positive charges are possessed by particles such as protons, which are in the nucleus of an atom. Now, charges of the same sign repel one another, so negative and negative repel one another, and positive repel one another. But dissimilar charges, positive and negative charges, attract one another. We also have electrically neutral objects. Now, these objects could be neutral because they have equal amounts of positive and negative charges, like in an atom, for example, which has an equal number of protons in its nucleus as it has electrons orbiting that nucleus. You can also, though, have particles that are fundamentally neutral, like the neutron, for example. Now, if you're talking more in depth about charges, then you can classify them by their interactions. So there's two broad classes of particles. There's hadrons, which interact through the strong force, and then leptons, which interact through the weak force. And by strong and weak force, of course, I mean two of the four fundamental forces of nature: the strong force, the weak force, gravitational force, and electromagnetic force. All right? Now, of course, the attraction and repulsion of charges from one another due to their sign, that's due to the electromagnetic force. But by interactions, I mean that inside the nucleus or inside of a hadron, for example, the strong force dominates, and it's the force that holds those hadrons together. All right. Now, hadrons are composed of quarks, and leptons are fundamental particles in and of themselves, as far as we know. So, protons and neutrons are hadrons. They're made of quarks, but an electron is a lepton, so it's a fundamental particle by itself. It's indivisible. It's already in its most fundamental component. Another fundamental thing that you should remember is that for every particle, there exists an antiparticle. For example, the antiparticle of the electron is the positron, and the antiparticle of the proton is, maybe not so originally named, the antiproton. And there's antineutrons and so on and so forth. One thing to remember about antimatter is that the antiparticle to a particle will have the same mass as the particle. So you can't say, for example, that the positron is the same thing as a proton. It's not the same thing. Its mass is the same as an electron, 9.11 times 10 to the minus 31 kilograms, right? So it doesn't have the same mass as a proton. So just because it's positively charged doesn't make it a proton. A lot of students find that kind of confusing. So a positron has the same mass as an electron, and it is a lepton, okay? But its charge is opposite. So the antimatter particle will have an opposite charge to the corresponding particle. So antiprotons, for example, have a charge of a minus fundamental unit of charge. Antiprotons have minus fundamental unit of charge, whereas the proton has plus a fundamental unit of charge. We'll talk more about quantization of charge in a second, but just for clarity, I'd like to go ahead and say now that the fundamental unit of charge, which I'll call E, is 1.602 times 10 to the minus 19 coulombs, and the coulomb is the SI unit of charge. Now, at present, physicists believe that the building blocks of matter are complete. This is known as the Standard Model, okay? So there's 6 quarks with their antiparticles, and these quarks make up all the hadrons, like protons and neutrons. And then there's 6 leptons with their antiparticles. And the electron and neutrinos, associated neutrinos, are leptons. Okay? If you'd like to learn more about this, there's further courses in modern physics that are available to you. And I have some online lectures posted about that if you'd like to watch them. When you're talking about hadrons, there's 2 broad categories of hadrons. You have mesons, which are composed of quark and antiquark pairs, and then you have baryons, which are quark triplets. Protons and neutrons are baryons. The proton is composed of 2 up quarks and a down quark, and the neutron is composed of two down quarks and an up quark. There's 6 types of quarks, as we said: up, down, strange, charmed, bottom, and top. Now quarks have a fraction of the fundamental charge. So for example, an up quark has a charge of plus 2/3 e, and a down quark has a charge of minus 1/3 e. So you can see that if you have 2 up quarks and a down quark, you would have plus 2/3 minus 1/3 of the fundamental unit of charge e, and that would give you a positive plus e charge. So that's a proton. If you had 2 down quarks and an up quark, you would have minus 1/3, plus 2/3, and so your net charge would be 0, and that's a neutron. Okay? So those are your quarks. Up and down, of course, are the most common in our everyday experience. They make up protons and neutrons, and the strange, charmed, bottom, and top are more rare. All right? Now, you don't often encounter, or ever encounter really, fractions of the fundamental charge in nature, like plus 2/3 e, because it's pretty much impossible to separate a proton and have it have any kind of lifetime. All right? It's indivisible. It doesn't decay. As far as we know, protons have a life longer than the age of the universe. So they're not going to decompose into fractions of a quark. And smashing them is really hard because the strong force is aptly named. It's really strong. And so anytime you try to break something up like that, you just get more quarks. They just create quark and antiquark pairs, and they don't really stick around. So for all intents and purposes, the fundamental unit of charge is it. You can't really break it up more than that and have it have any kind of lifetime. That brings me to the next point, which is that charge is conserved, right? If you're talking about an isolated system, then the electric charge is always conserved in that isolated system. For example, I have a picture here of a kid's hair sticking to a balloon, and hopefully we've all done this experiment. If not, you should go out immediately and do this. Okay? You take a balloon and you rub it on your head, and charge is transferred back and forth between the balloon and your head, and your hair gets all charged up. And then it wants to stick to the balloon because, of course, you've transferred charge from your hair to the balloon, so they're going to have equal and opposite charges, and that's a strong attractive force. Okay? And so your hair will stick to the balloon. You can also take your charged balloon, if you like, and stick it to the wall. Because of the induced surface charge from the wall, it'll pull the charge apart. The net charge in the balloon will pull those charges apart, and then you can get a dipole charge interaction on the wall, and it'll stick there. So that's kind of fun. But it's important to realize that you're not creating charge when this happens. You're just transferring it from one object to the other. Okay, the hair to the balloon or the balloon to the hair. I can never remember which way that goes. I can never keep it straight in my head. Sorry about that. But anyway, you're transferring charge through. Now, when you talk about conservation of charge, it's important how you define the system. Because if you just define the system, say for example as your hair, then it does kind of look like charge has been created. And so when you set up problems, it's important to understand and define your system carefully. You should define your system as hair plus balloon, for example, and then the conservation of charge works out. Now some of you are probably sitting there going, but you can create charge. I know about it, I learned about it. It's called pair production. Or maybe you can destroy charge, and it's called pair annihilation. It's important to understand when you're talking about this that it's the net charge that we're talking about, okay? In pair production, what's happening is you start off with a photon or a particle of light that's very high energy, like a gamma ray, and then you pass it through a target, like a thin lead sheet or something like that. When the photon passes by the nucleus of the lead or whatever that you're passing it through, then it will decay and it will annihilate and it will become a particle and its corresponding antiparticle. Now, in theory, it could create any particle-antiparticle pair at once, but since the electron and the positron are pretty low energy, right, then usually that's what's created. So you get an electron-positron pair for that gamma ray photon that passes by. Now, because the electron and the positron have equal and opposite charges, the net charge of the system is 0. So you start off with a photon, which has a net charge of 0, and the electron and positron also combined have a net charge of 0. So you've not created any net charge, right? You've created charges, okay, but the net charge of that system is still 0. So that's what we mean when we say conservation of charge. We're talking about net charge, all right? So it's important to understand that. If you want to, you can find more about ideas like pair production in further lectures and studies in modern physics. It's a very interesting topic, but for now I kind of have to leave off here. Satisfy it to say that energy is also conserved. So the energy of the gamma ray goes into creating that mass energy of the particle-antiparticle pair and gives some to any kinetic energy that might be left over. Now we also say that electric charge is quantized. As I was saying earlier, it's pretty much impossible to get any net charge less than the fundamental charge of an electron. For example, 1.602 times 10 to the minus 19 coulombs net. So any kind of net charge that you have is going to be an integer, we'll call that n, times the fundamental unit of charge, 1.602 times 10 to the minus 19 coulombs. Now, if you have a lot of charge, it could be a very large integer, okay? And then if you get up and towards big charges, then it can start to look continuous. But that's just because the fundamental unit of charge is so very small. So we can say that any net charge Q, we often use Q for charge symbols in physics, Q is equal to some integer number big N times the fundamental unit of charge E. Now this charge can be positive or negative because there's those two types of charges plus the negative charges. And so whichever one that you have in excess of, that's what you choose. All right. There's other units for charge. The Coulomb is the SI unit of charge, but there are others. For example, in the CGS system of units, they often use the electrostatic unit or the ESU. If you need to convert back and forth between the SI unit, the Coulomb, and the ESU, 1 Coulomb is 3 times 10 to the 9th ESU. So that's a pretty easy conversion to make. It's worth noting that the Coulomb is an enormous unit. 1 Coulomb of charge is a lot of charge, and so sometimes the ESU might be a more convenient unit for everyday type charges. Oftentimes in physics problems we'll refer to the term point charge, and that's a particle that has net zero size that still carries an electric charge. It's also worth saying that the behavior of electrons and protons is well modeled by describing them as point charges, and that's because they're so very small. As far as we know, the electron really is a point particle. Its wavelength nature, the de Broglie wavelength, kind of dominates over any probing that we can do. And so as far as we know, it's a point particle. But the proton, we know, has, from collision experiments, has a radius of about 10 to the minus 15 meters. And as you know, that's really small. Atoms are on the order of, say, 10 to the minus 10 meters. Okay? And so 10 to the minus 15 is teeny weeny. And so you can treat the proton as a point charge as long as you're not really getting down into the down and dirty with the really super high energy quantum mechanics. Okay? So for classical physics, calling protons and electrons point charges is absolutely fine. Now I'd like to talk about Coulombs Law, which is the equation that describes how charges interact with one another and the forces that they exert on one another in electrostatics. And so Charles Coulomb is a French physicist, or was a French physicist, who lived in the mid to late 1700s and early 1800s. And he made a lot of contributions to electrostatics and magnetism. What he quantified and laid out in Coulomb's law is the electrical force between two stationary point charges. He found that the force is inversely proportional to the square of the separation or distance center to center between the 2 point charges. We'll call that R. It's a pretty common choice. And it's directed along the line joining those 2 point charges. So if you draw a line center to center between 2 point charges and connect it, the force will be parallel to that line and acting along the centers of the point charges. The force is also proportional to the size or magnitude of those 2 charges. So if you have a larger amount of charge, you have a larger amount of force. And so it's going to be proportional to the product of those 2 charges. I'll call them Q1 and Q2 for simplicity, and because it agrees with your textbooks. Most textbooks, actually. The force is, of course, attractive if the charges are of opposite sign, and it's repulsive if the charges are of like sign, and it's a conservative force as well. If you want to find the magnitude of that Coulomb's law force, it's given by this equation right here. The force F is equal to the Coulomb constant, which is often indicated with a K, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. It's a pretty large constant, okay? And then times the product of the charges, Q1, Q2, and then divided by the distance in between the two charges, center to center, r squared, all right? Now, the Coulomb constant is often written by convention as 1 over 4 pi epsilon naught. Epsilon naught is the permittivity of free space, and that's 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. So sometimes instead of K, you'll see 1 over 4 pi epsilon naught, Q1, Q2 over r squared. Remember that when you plug into this law, if you want your force to be in newtons and you're not using CGS units, for example, where you'd be looking for the dyne, okay? So if you want your force to be in SI units in newtons, the charges need to be in coulombs. The Coulomb constant needs to be written as 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, and the distance r needs to be given in meters. Remember that, as I said, Coulomb is a ridiculously large unit of charge. Everyday charges are more on the lines of microcoulombs to nanocoulombs, somewhere in there. And so you'll need to remember your SI prefixes, micros 10 to the minus 6, nanos 10 to the minus 9, and plug it in this expanded form when you do that. Also remember that force is a vector quantity, and so you're going to have to remember your vector stuff. You're going to have to know how to break a vector into its component parts, and so on and so forth. So if you need a review on that or a refresher on that, there's other videos and other resources for you to remember those things. I'm not going to cover them in too much depth today. I'm going to assume that you still remember and understand that. Okay, so force is a vector. So generally how we write Coulombs law is in vector notation. The equation before just gave you the magnitude of those two charges, or of the force. So in vector form, you would put your force vector with either the arrow on the top or in bold or both to indicate that it's a vector. And then you would have the Coulomb constant times Q1, Q2 over r squared, and then that r hat there, r hat is a unit vector that points along the radial line, r for radial I guess, that connects charge Q1 to Q2. Now in this picture that I show here, there's two positive charges, and because they're like charges, they're going to repel one another. So the vectors F12 and F21, that's the force, F12 indicates the force on charge 2 from charge 1, okay? And that's going to be acting on charge 2, pointing away from charge 1, kind of up and to the right there, okay? Now, Q1 is the force on charge Q1 is F21, the force from charge 2 on charge 1, in other words, and it's pointing down and to the right. So you can see that there's a dashed line that connects charge Q1 and Q2, and F21 and F12 are parallel to that line, okay? Because it's repulsive, they're pointing away from one another, all right? So that's how that goes. R hat unit vector points along that radial line, and then what you would do is you would find the magnitude of that, you would break the vectors into its component parts, and then you would let the direction be dictated by the vector notation there, okay? This is an action-reaction pair. So the force that charge 1 exerts on charge 2 and the force that charge 2 exerts on charge 1, those two forces are equal in magnitude but opposite in direction. As we saw back there on that drawing, you can see that F21 and F12 have the same length. Those two blue vectors have the same length to those vectors, okay? And they're pointing in opposite directions. The arrowheads point in different directions away from one another. If you have dissimilar charges, like charge Q1 and Q2 in this picture, the positive charge is indicated here in orange, and the other charge is indicated in blue, then you do a very similar thing. You draw your dashed line connecting the center to center of the two charges, but now the two forces acting on the two charges point towards one another. Still notice that they're equal and opposite. F21 and F12 point in opposite directions, and the vectors are indicated as the same length. Remember that when you're trying to draw these sorts of things, it's very handy if you let the length of the area you draw represent the magnitude of the force. So in this case, those two arrows should be the same length as one another. If for some reason you had multiple charges, for example, like in an example that I'll do for a minute, it's handy on your drawing if you remember that you need to draw longer arrows for larger forces. Okay. Okay, now the sign of the product Q1, Q2 gives the relative direction of the force between Q1 and Q2, okay? So if you multiply the two charges together and you get a net positive number, then you'll know it's supposed to be a repulsive thing because the two charges are the same. If you multiply a positive charge times a positive charge, you get positive. If you multiply negative times negative, you get positive. And so that would indicate with a positive number that the force is repulsive. However, if you multiply a positive charge times a negative charge and you get a net negative number, well, that means that it's attractive and they need to point towards one another. Other than that, though, the sign of that product doesn't really do anything for you. And so in the steps that I'll outline in a second, I'll tell you to just calculate the magnitude of the force, draw your picture, and then don't leave the negative signs in any other way when it comes to the charges, okay? You worry about the sign when you resolve that vector into its component parts, okay? If that's confusing, hopefully in a second it'll become more clear when I show you the example problem. Another important thing to remember is that if you have more than two charges, then you're going to get a lot of different forces acting on one net charge. For example, if you had a collection of 4 charges, charge 1, 2, 3, and 4, then the net charge, the net force on charge 1 would be equal to the sum of the forces from all the other charges acting on charge 1. We would write that mathematically as F1, or F total, would be equal to F21 plus F31 plus F41. In other words, charge 2, 3, and 4 are all exerting a force on charge 1, and you would have to sum those forces up to get the net force on charge 1. This is known as the superposition principle. And so anytime you have a force that obeys the superposition principle, then what you do is you just do the vector sum of all the forces from all the objects acting on it. Okay? You might have seen this in another class. For example, if you were calculating gravitational forces from a system of particles or something like that, it also obeys the superposition principle. In physics, the superposition principle is often obeyed, and it's really usually only when you start getting into quantum mechanics that you see it break down. For example, angular momentum addition, it doesn't obey the superposition principle as such. There's certain rules that you have to do when you add angular momenta, and it's not just a simple net sum, okay? And you'll learn that later if you haven't already. And if you haven't learned it already, don't worry about it yet, you'll get to it. Okay, so let's talk about the superposition principle in a couple of simple drawings, and then I'll show you a more involved example. So here I have a collection of 3 charges, and the problem must have asked what the net charge on charge, or net force on charge 3 is. Okay, so see here in this picture, charge 3 is in the upper right, it's a positive charge, and then charge Q1 is at the origin, and charge Q2 is along the y-axis. These 3 charges form a little triangle, okay, and you can see that F23 is the attractive force that's exerted on charge 3 by charge 2, since they're dissimilar charges. So F23 points along the x-axis towards the y-axis, okay, it's an attractive force. Whereas charge 1 and charge 3, well, they're similar charges, they're both positive, and so F13 points away from charge 1 along the line connecting them. And then what you have to do to get the net charge is to do the vector sum of F23 and F13, okay? So let me do a more involved example now, and I'll take you through it. I have a specific strategy that I like to use when I'm working these kinds of problems, and I like to kind of break my thinking up into 4 steps, and so I'm outlining that strategy here. But first, let's go through what the problem asks you to do. This example problem shows you an equilateral triangle with a charge at each corner of the triangle there. So you have a +2 microcoulomb charge at the origin, you have a +7 microcoulomb charge at the top of the triangle, and then you have a -4 microcoulomb charge on the bottom right of the triangle. Now, the problem asks you to find the force on that negative charge, which is at the bottom right. The equilateral triangle has lengths of sides 0.5 meters, or ½ a meter, and of course all the internal angles for an equilateral triangle are going to be 60 degrees by definition. Okay, so here's my strategy. What I like to do when I'm doing these kinds of problems, like I said, is break it into 4 steps. Step number 1 is always to draw a picture and include the force vectors as arrows on that picture. So for whatever charge in question that it's asking about, here it's asking about the -4 microcoulomb charge, I'm going to draw the force vectors from the other charges acting on that charge. I'm going to do my best to make the arrow lengths representative of the magnitude of the force, and I'm going to put arrowheads on there that indicate the direction of the force so that I can keep it straight. And when I draw them, I'm also going to label what my angles are there. Okay, that's step one. In step two, I'm going to take the magnitudes of all the force vectors that I've drawn. I'm going to write those magnitudes down, okay, using Coulombs Law. Then in step three, I'm going to take those magnitudes and break the magnitude of those vectors into their vector components. Okay? To do this, I'm going to take the magnitude that I found in step two and multiply it times the appropriate trigonometric function for the angles that I found in step one. Okay, so I'm going to resolve those into their vector components. And then finally in step four, I'm going to add up all my x components and all my y components for the force vectors on the charge in question. In other words, I'm going to apply the superposition principle to solve for the total force on my -4 microcoulomb charge. So those are the steps that I'm going to follow. Ready? All right, here's step one. I've drawn my force vectors here in red, okay? Now, as you can see, the lines of the equilateral triangle are already drawn for me, and so that makes it a little easier. All I have to do is make my force vectors lie along those lines connecting the charges. So that's nice. Now, on the 4 microcoulomb charge here, I've got my negative charge and my positive charge. So those are dissimilar charges, and so the force on the -4 microcoulomb charge is going to point towards the 7 microcoulomb charge there. Now, I can see here that the 7 microcoulomb charge is larger than the 2, so I've made my force vector for the -4-7 interaction longer than the other interaction. You can see that there to represent the fact that this is a larger force. So here's my vector pointing along the line connecting the -4 to the 7. It's longer than the other one, and I've also labeled the angle there. It might seem a little redundant since we kind of know what this angle is already. It's an equilateral triangle, so it's got to be 60, but it is one of my steps, and I don't like to skip my steps, so I've done that here. Sorry. Now the other one, the other force vector, represents the force in between the -4 microcoulomb charge and the 2 microcoulomb charge. It's a shorter vector because the 2 microcoulomb charge is smaller than the 7, and so it would exert less force. It connects along the line, joining the -4 to the 2, and it points towards the 2. Since these are dissimilar charges, it would be an attractive force. Okay, so that's my step one. I've drawn my force vectors. Now it comes down to step two, which is writing the magnitudes for those forces. You'll notice I leave the signs out here. That's because I only want to write down the magnitude of the force, okay? Remember that when you start getting into forces and vectors, the sign of the force indicates its direction. Well, when I draw the picture here, I've already taken care of the direction. And when I resolve it into the vector components using the trigonometric functions, that's where I'm going to put my minus signs in the final step. So in step two here, I'm just writing down my magnitudes, okay? Now, I've written down F7,4. That's the force from charge 7 on charge 4. Okay, so I'm going to calculate the magnitude for that. Coulombs law is K Q1 Q2 over R squared. All right, so K, the Coulomb constant, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. I wrote it here as 9 because I'm just keeping one sig fig here. So 9 times 10 to the 9th Newton meters squared per Coulomb squared times the product of the magnitude of the charges, 7 times 10 to the minus 6 coulombs times 4 times 10 to the minus 6 coulombs, since they're microcoulomb charges, and then divided by the distance in between the two charges squared, which is half a meter squared. When I solve this problem, I get 1.0 newtons here, okay? So that's my force, 1.0 newtons. And then for my left charge, sorry, let me fix this, 0.3 since I'm keeping just one sig fig. For my left charge, I'm also going to calculate my magnitude. F24 is 9 times 10 to the 9th Newton meters squared per Coulomb squared times the magnitude of my two charges, 2 times 10 to the minus 6 times 4 times 10 to the minus 6 coulombs, divided by the distance in between the two charges, which is half a meter squared. Okay? And that gives me a net force of 0.3 newtons. Okay, Now that I've calculated the magnitudes of my charges, it's time to move on to the magnitudes of my forces. It's time to move on to step 3, which is resolving those magnitudes and putting them in vector notation and putting all the right components together. Okay? So step 3. If you look here at F24, it's easier to resolve into components than F74. The reason is that F24 obviously points here only along the x-axis. It's parallel to the x-axis. And that means it's not going to have a y component. And so it's really easy to write this in its vector notation. Now, I'm using the notation for unit vectors. X hat for the x direction, y hat for the y direction, and z hat for the z direction. I realize that other textbooks might use different notation, I hat, j hat, k hat, or what have you, but this is the notation that is common in a lot of books that I use, so that's what I'm going with. Okay, so F24, written in vector notation, it points in the negative x direction, okay? And so I'm going to put a minus sign out front. See, this is where I put my minus signs in. They indicate the direction. So since this vector is pointing in the negative x direction, that's when I put my negative sign out front. So I have minus 0.3 newtons x hat, and that's F24 written in vector component notation. All right? Now, F74 is a little harder because it's got x and y components. Okay, so what I've got to do is break that vector into its component parts. Now the angle here on the inside of this triangle is 60 degrees. And so that means that since that angle is with respect to the x-axis, okay, then the adjacent side, which will be the x component, I'm going to use the cosine for. So I have the magnitude of my vector, 1 Newton, times the cosine of 60 will give me my x component of that. Okay? Like I said, if you need to go back and review some trigonometry and how to break vectors into their component parts, there's other resources on the web for that, and I have an online lecture myself if you'd like to reference it. Okay, so here, 1 times cosine of 60. Now, that vector points up and to the left. Left is the negative x direction. So I put in a minus sign here to indicate that it's pointing in the left way, okay, leftwards. So minus 1 Newton cosine 60 x hat. That's the x component. Now if you use cosine for the x, you're going to use sine for the y, okay? If you use cosine for one, you're going to use sine for the other. So since here the y component is pointing upwards, then it's plus 1 Newton times sine of 60 y hat. All right, so that's how you break that into its vector parts. Multiplying times the cosines and the sines times the 1, I end up with F74 equals 2 minus 0.5 newtons in the x hat plus 0.9 newtons in the y hat, keeping one sig fig. All right, I've resolved my vectors into their component parts. That's step 3. Now for step 4, I'm going to apply the superposition principle. It's important to remember that this is vector addition. So you don't just take the magnitudes and add them together. That way lies peril, okay? If I did that, then I would say that the net force acting on the 4 microcoulomb charge is 1.3 newtons, which is incorrect, okay? That's incorrect. What you're going to do is you're going to add the components. You add the x to the x and the y to the y. So looking at F24 and F74, the x component of F24 is minus 0.3 newtons, and the x component of F74 is minus 0.5 newtons. So the net x component of my total force will be minus 0.3 plus minus 0.5 newtons. Okay? That gives me a net x component of minus 0.8 newtons in the x hat. So see, I did my summation component-wise. Now, for my y component, my F24 doesn't have a y component, so it's 0, and then F74 is plus 0.9 newtons. So my net y component of that vector is going to be 0 plus 0.9 newtons, which is 0.9 newtons. Okay? So now I have my net force vector for the force acting on my minus 4 microcoulomb charge, and that's minus 0.8 newtons x hat plus 0.9 newtons y hat. All right. That's how to do those types of problems. That's a simple example, but it'll get you started, and I hope that helped, and I'll see you in class.